All right. So let's look at number one. If you want to follow along with your homework, feel free. If not, just start working on it when you can. So find the distance traveled in 20 seconds by an object traveling at a constant velocity of 16 feet per second. Decide whether the problem can be solved with calculus or pre-cal. Okay, what do you guys think? Can we could you find the distance traveled, which is basic pre-cal? Or do we need calculus for this? Yeah, I think so too. Let's see. Looks like it. Now, do you see why though? Look at number two. Same question, but this one's clearly different, right? Velocity is not a function. It is not constant. So if it's constant, yeah, you can just plug in a number, multiply whatever by 20. Who cares? This velocity will depend on time. It's not always constant. So this is a little more complex. So once you have functions that are changing, velocities that are changing, things that are more complicated, that's when you need to start thinking about calculus. Does that make sense? Number three, a bicyclist is riding on a path modeled by this function here. Okay. It's just a basic line, right? Slope is 1. I'm sorry, slope is 0.09. It's a linear power 1. Where f(x) and f(x) are measured in miles. Okay. Find the rate of change of elevation. Is the change constant along the entire line? Or does the rate of change different at different times? In this case, x is miles. So yeah, since it's constant, we don't really need to think about derivatives or any of that stuff. So it should be pre-cal. Since this slope is constant. Now, if you had like a quadratic, right? Check this out here. Try to picture the difference, right? So you had some random parabola. Over here, if you go left to right, if you think back to college algebra, right? Going left to right, you're decreasing. But over here, you're increasing. You see what I mean? How the rate of change of the function itself is not constant. It is different depending where we are at. This guy is always the same rate. That's the difference between, okay, when I want to look at a rate of growth, rate of change, that type of stuff, if the function becomes more complex, then I need calculus to help me. Okay. It's not like algebra. Well, okay, yeah. The rate is just the slope. Who cares? Do you see the difference and why where we're headed with calculus? The point of it, right? This is a clearly not constant, right? You see that? So right here at this section, let's say from here to here, if you were just to eyeball it, is my rate negative or positive? Rate of change here. The growth, rate of growth. if this was yeah, clearly it's negative, right? We're increasing for a while, then suddenly you start going down. So if we were to use calculus, all the slopes tangent to these points would be negative. All the slopes over here, right? If you drew points and put lines right next to them, slopes would be positive. Over here, they'd be negative, which we'll go into in depth later. But that's the big picture, right? Why we care about calculus. At the end of calculus, chapter 5, the beginning of Cal 2, we started thinking about area. Yeah, it is. Do you see why, or do you see which one requires calculus and why it does? But comparing A and B. Yeah, for sure, B needs calculus. Do you see why? Yeah, pretty much. This guy can be solved using just basic geometry, right? This cannot be. You can approximate it. You can approximate B kind of an idea. Like I could draw, right? Technically, I could draw a square around it. Yeah, it was kind of, it's going to be close to this, right? Not accurate, but close. But it's not correct. Here, I can just use geometry. It's just a triangle. So this requires calculus to find the exact area. Okay. That's why it starts becoming important, because in real life you start having really strange shapes. Nothing ever, not, the real life is not perfectly geometrical all the time. It's not moving in a perfect straight line all the time. It's not constant. Things are messy and complex, right? Hence why we needed calculus. Alrighty. Anyway, let's see here. Eventually, they talk about integrals and this idea of summing many, many rectangles. So they figure, okay, well, if I want to find the area, like let's say underneath this, you draw a bunch of rectangles underneath. I can't draw underneath like sausages. And if you get skinnier and skinnier rectangles, eventually it becomes perfectly smooth. If you picture the width of these rectangles becoming infinitely thin, infinitesimally, right? Then it becomes smooth. So that's the whole idea of the integral, why we have to talk about limits, and why we introduce them at the beginning of calculus. So limits is required for these ideas, these theory questions. Okay. So that's a big overview as to, that's basically a preview of calculus. Okay. Is there any questions on the big picture? I'm going to open 2.2. We're going to start limits. Here we might actually have to solve stuff. Okay. No, we're moving on to 2.2. Is that cool with everybody? Probably gonna need Desmos. Let's see here. Close this. I think this will help us see what's going on. Okay. And just so you know how I'm going to present the material, right? I'm going to assume you read the book, you looked at the theory, you looked at the videos I've posted. So when we get together, right, I'm going to show you how to solve problems, how you do it, how you do the homework, how you do the test, how do you get the answer. So that's what I'm going to show you. The theory, I'll try to spend some time on it, but I expect you to read it on your own too. Okay. That way you get more out of it. So I'm hoping, well, since you got the book a little late, I'm not gonna judge you if you didn't read the first section. It's okay. Um, the idea of limits, right? It's the definition is very, very complicated, but the idea is pretty straightforward. Okay, so when you see this notation here, so this right here is your function. Consider this f of x. So this guy right here is your f function. Okay. This notation limit with the arrow there is telling you allow x to approach 8 and go infinitely close to 8. Let x go to 8. So the question becomes, okay, what is the function doing from both directions as I approach 8 from 8 as I approach 8 from the left? See how they're getting closer and closer to 8 from the left, meaning below 8, right? So if I have a, let's say 8's right here, as I get closer and as I get closer to 8 from the right, sorry, left, and from the right, what is the function doing? That's what they want to know here. That's the question. All this fancy notation, they want to know what does a function do as it goes to 8? So in the homework, you're going to plug these into here, to the x value, and just put them in your calculator and find out, okay, what is the answer? The output goes here and here, right? So you're going to see from the left side is approaching a number. And then you do the same thing on this side. You plug in 8.1, 8.01, 8.001, and you find out, okay, well, what number am I approaching from the right? Is it the same number? Right? If it is the same from both directions, I'm approaching some y value. I don't know what it is. So as I get closer and closer to the 8, I'm getting closer and closer to some y function, some y functional value over here. That makes sense? So this corresponds to this guy. This corresponds to this. So as I get closer from both directions, I'm closing in on some y value, assuming the limit exists. If they are not the same, then the limit does not exist. Okay, so let's look at this as a graph. Let's see if I remember what it is. The picture makes this all make sense, in my opinion. I don't know what it was. Just guessing. It's close. All right. So I'm going to graph a vertical line at x equal to 8 so we can see what the function is doing there.
It's just a 1 plus.
There's a plus on top?
No, in the bottom. It's 1, it's 2 plus. You were 2 plus.
Plus x squared. This one, right?
Yes, it's only 1.
Oh, I see what you're saying. Thank you. Thank you. Okay. And it was positive 8, correct? Yeah. Minus 8, x squared minus 9x plus 8. Okay. We're good. X equal to 8 is right here. So it looks like there's some value here, right? So as I come from the left side, right, this is the negative side. the y value is going to, looks like 0.14, right? As soon as I get there, though, what happens?
It says undefined.
Yeah. So the limit could exist if these values are the same, 0.14 on both sides, 0.143 or whatever. 0.143 looks like, right? So right before it gets to 0.143, it jumps to undefined. So the functional value does not exist, but the limit does exist. So as you plug these values in, you're going to get closer and closer to point, what did I say? 314, right? 143. So that's what's going to be happening here. It'll be getting closer and closer to that on the left, closer and closer to that on the right. Whatever number is close to both of these is what goes here. That is what a limit is. It is the functional value, in other words, the y value of the function as it approaches a specific limit, a specific x value. Does that make sense? Graphically, what a limit is?
Yes.
Now, if you read the book, it might be a little complicated. You got to be specific. Okay, what is it? See, this is the definition we learned as a math major. It's very complicated looking. And it took me a while to understand what the heck they were saying. But essentially, the way I explain it to you is all it is. So all this right here, right? When we're talking about infinite limits, or maybe just general limits, it's the same thing. Similar definition, right? So basically, as your function approaches some epsilon, the limit will approach some delta within some delta range. Okay. So reading this definition in the book can be a little intimidating, as you can see, but it's not too bad, right? You just told me right now that you understood it. It's literally this. As I go from the left, it approaches some y, and from the right, it approaches some y. If they are the same, you say it exists. Okay. But don't be intimidated by reading the book. Although this becomes very important if you go deep into math. Anyway, any questions on number one?
So what do we put in the box for the first question?
Here?
Yes.
Whatever these two approach. So as we get closer and closer, I think on my graph, it was like did I say 143? That was?
Okay.
I don't remember. Let me see. 0.142. How many decimal places? 4 decimal places. 1429. So as you plug them in here, you'll see that it's going to 1.14, 1.4 something, 1.4 whatever, closer and closer to something like this. Okay. So both sides will approach that same number. Just like I showed you graphically, this is how you do it. This is one technique to find the limit using a calculator. Basically, you're just crunching the numbers instead of looking at a graph. Yeah, no, right. Okay, so you'll do the same thing here. Just like, all right, well, what is this is 3, I think. Cool. Okay. For number 2, there is a definition in the book. So if you look at the book, you should know that the limit, pretend this doesn't exist, that 3. The limit of sine x over x as x approaches 0 will always equal to 1. Okay. And that is proven in the book using something called a squeeze theorem or a sandwich theorem. So basically what they do is they squeeze the sine function between two similar functions, and they're like, okay, I know the limits of these two, and since sine is in between, then that means that one has to be the same. Okay. And it's a very complicated proof. I'm oversimplifying it, but they prove that this will be 1. So if we treat it like a formula, since we know this piece is 1, right? 1 times 3 would be 3. That's how I knew the answer. But they still want you to crunch the numbers. So plug in these values and then find out what they are. Okay. Just like this last example. Let me see if I can find the squeeze theorem for you. It's in the book. This is just a little faster. So this is the theorem in the book. Either it comes out in this section a little later. So they squeeze the f function in between two others. So if we know, right, the theorem says, if we know the limit of g and h, and they're both equal to L, and it's squeezed in between those two, then this one has to also be L. So that's how they prove and create this formula. Okay. It's a lot more involved, and it'd probably take me 40 minutes to show it to you. So if you're curious, just look into it. If you want to see it, maybe another time. All right. So far, do you see what we're doing? You guys still with me?
Yes.
This is the computational method for finding a limit. I also showed you how to do it graphically. I showed you 2 techniques really quickly, but we're going to keep using them. Yeah, I stopped doing the proof way because it takes a lot of time. And at the end of the day, I'd rather use my time to show you how to do this. I'd rather you use your time to learn the theory. That way you don't get stuck when you're doing tests or homework. Okay. Check this guy out. Number 5. And I'm not writing any notes because it's not too involved right now. So again, this is my f function right here. 6 minus x. That's f of x right there. So as the limit of x goes to 2, what is a y value doing? So what you should always try to do is just plug in 2.
It would be 4.
Yeah, so there's nothing stopping from me subtracting 2, right?
Yes.
So I plug in 2, 6 minus 2 is 4, which is right here, right? When the limit approaches 2, the y values are going to 4 from the left, 4 from the right. So you see how it's still the same thing, it's just that this one's super easy, but I still want you to think of it in terms of limits, right? What is the y value approaching? It's approaching 4, not because 6 minus 2 is 4, but because graphically the left and right side limits are going to 4. Therefore, the limit is 4. I know that sounds strange, but that's what we're doing, okay? So number 5 makes sense?
Yes.
Check this one out. Here we have a functional value that's down here, but undefined over there. You guys remember piecewise functions back in what's it called? College algebra? Maybe even before that. So what this is saying is when x is equal to 1, it's always going to be this, no matter what. And that number is 1. So if x is 1, then y value is 1. That's how you use that. If for any other value, if x is not 1, so anything else you plug it in here. So if I choose x equal to 0, well, I'm going to plug it into the parabola. If I choose 3, then I plug it in here. That's why I have a graph like this for every other x. And then all of a sudden I jump to here when it's 1. Then I go back here, right? So that's what the piecewise function is doing. Yes, you're basically gluing two functions together. One's a parabola and one's just a point, okay? So the limit of this function f, as we approach 1, here's 1, right? As you get closer and closer to 1, what are the y values getting closer to? Right.
2, I guess.
Looks like 2, yeah. Right? Just that I can't draw very good. Okay. So the limit is going to 2 from the left and the right. From the left, I mean the negative side and the positive side. So you would say, well, the limit is obviously 2, right? Because
Yeah.
it's the same on both directions.
Mm-hmm.
But the functional value is not the same. Do you see that in this case?
Yes.
So here the functional value is 1, but the limit is 2 because of the piecewise function. Anyway, the rest are similar, just different kinds of functions. So you'll do the same thing. Check out number 8, though. This is f. So as the limit of f goes, as x approaches 0, does this limit exist? What's wrong with it? From the left side, the y values are going to here. From the right side, the y values are going here. What does that mean?
Maybe it's not exist.
Yeah, they have to go to the same place. The left and right must be equal. Otherwise, there is no limit. Okay, there is single-sided limits, which we'll talk about in a different chapter, but there is not a regular limit. Yeah, you would enter DNE. And on an exam, you would explain why it's DNE, right? You would say the limits from both directions, or use the math notation to say limit on the left is not equal to limit on the right, therefore the original limit does not exist. You use English or math symbols, I don't care. As long as you understand why. The first test is a little more theoretical. In the first two sections, as you can see, there's not really much to solve. It's more like conceptual. But there is things to work out in the next section, but this is the most theory-heavy chapter in Calculus 1. It's not a bad thing, it's just how it is. Okay, so here they want to know what is the function at 1. What is the y value? It would be, so 1's right here, right? So there's a hole here and a hole there, so it has to be here. So I would say it is 5, right? The function at 1. Do you remember what this notation means? I'm assuming everybody does, but if you don't, let me know. Let me know if you don't remember. If you see this, you know what I'm asking. Yeah, right?
I don't remember. If you can explain it.
Okay, so for example, let's say I had a function called f of x equal to x plus 2. F of 0 means plug in 0 and give me the y value, right? So this notation is asking me, what is the y value? Well, the y value is 2. Graphically, this means you have a point at 0, comma 2, x, comma y, right? Do you remember?
Yeah, I remember now.
So this is asking for the y value. This is f. So f of 1 has to be right there. 5. Does everyone agree that it is 5?
Yes, it's 5.
Does that make more sense? Okay. So make sure you ask questions. That way I can give more details. So that's why you're here. Limit of f as x goes to 1. Well, 1's right here, we said, right? So from the right side, it's going somewhere. From the left side, it's going over here. So what does that tell us about the limit of this function? What would you put here?
B and E because it doesn't exist.
Yeah, they're not the same, therefore it does not exist. Single-sided limit exists. The limit from the left is equal to 7. Limit from the right is equal to 1. But since this is 7 and this is 1, they are not equal, therefore D and E here, right?
Yeah.
You see what I'm saying? All right, f of 6. We just explained what that means, right? What is it?
So you're saying it's 6?
Yeah, it looks like when x is 6,
I think it's 5.
there's a hole there, right?
Yeah, that looks like an open.
So I would say it doesn't exist. Because at 1 we got 5.
Mm-hmm.
Over here it's undefined. I want to say D and E, but we'll check in a sec. But what is the limit as we approach 6? From the left and right. What are the Y values doing?
Lower to 5.
So the limit is 5. The function of value wants to be 5, but it's not. So let's see. I don't know. 5, D and E, D and E, 5. Hopefully that's right. Let's see if I forgot anything. Does everyone understand why this is true? Does it make sense?
Yes.
I don't understand why C is doing it. I just don't understand the open dot and this thing.
So if you see it open, that means the function is not defined there.
Okay.
It's just a hole. Like, for example.
Yeah.
So that's just kind of saying like that's where it ends.
Yeah, like, oops. Like here we know that we cannot plug in -4, right?
Yes.
So basically, in this case, it's not a hole, it's just undefined. So this is an asymptote, and the other one, it was just removed purposely.
Mhm. Thank you.
Yeah. Yeah, pretty much. It doesn't exist, so. All right. Here, it's the same as number 10, it's just a little bit more in depth. The function is all this right here. So f of -2, here, it's right here. Do you see the asymptote situation?
Yep.
So what would you do?
Linear again.
Yeah, exactly. It's just like the one I graphed right now, right?
Mm-hmm.
It's not exist. But what about the limit? The limit sometimes exists. So I approach -2 from the left and from the right. What's going on? You're clearly not the same, right?
Yep.
So even if they had a value, they're not the same. The other one's shooting up to infinity. The other one's shooting down to -infinity. So D and E, right?
Yes.
F of 0, does that exist? What
No.
is the Y value?
It's 3. No, it's I think 2.5.
Yeah, 0 is right. If the X is here, what is the Y value?
Or okay. I got
Right?
it. Yep.
Yeah. So just go to the X and then see what the Y value is. That's all.
I saw the open dot, that's why I said it's 2.5.
Yeah, it's trying to trick you a little bit. It wants you to think about it.
Yeah.
So yeah, be careful. As we approach 0 from the left, oops, from the left and from the right, they're not the same, right? So part D, it's going to be D and E again, yeah. Is this making sense? It's not too bad, right?
Yep.
There's a lot of theory behind this stuff we're talking about. So make sure you read it a little bit. All right, this is similar, so let's move on to something else. All right. Well, it might be good. Let's see. Yeah, just whenever you get a chance, just look at the videos I posted. I think that it's one of my friends, or maybe the book itself, I forget. Going more in depth into theory. Okay. So we are a little ahead. I needed to figure this out for next time. So next time we'll talk about this because it's mandatory, and we'll do that. So on Tuesday, we'll do this guy, and then maybe 2.3. Okay. So for the next 30 minutes or so, let's try working on your homework. And we'll stop the lecture here. Let me take roll.